3.3 optimization problems. Okay, so let's start with what is optimization. Optimization is the process of optimizing a situation, realizing the best possible outcome, subject to a set of restrictions. Okay, so what we're going to do is like solve for the maximum or minimum, such as we'd want to solve for a minimum if we're minimizing a cost of making maybe a table or chairs, given a certain amount of material. Okay, and the domain is usually restricted, such as time, amount of materials, cost, as in like the budget, right? Money, budget. Okay, and etc. So example 1, we'll dive right in. A farmer has 800 meters of fencing. Okay, immediately I'm thinking perimeter. 800 meters of fencing would be the amount of fencing going maybe around. Okay, around something. And immediately I think rectangle, but I'm not actually sure of that yet. So I'm going to keep reading. And wishes to enclose a rectangular field. There we go. One side of the field is against a country road that's already fenced. Okay, so here's going to be the road, right? And that road already has a fence on it. So now we have 800 meters of fencing, but what we have to do is we actually only have to fence in these 3 sides to make a rectangle. That was already fenced. Okay, so the farmer needs to fence only the remaining 3 sides of the field. The farmer wants to enclose the maximum possible area to use all the fencing. Okay, so how does the farmer determine the dimensions to achieve this goal? So maximum possible area, whatever he's putting in here, maybe livestock, he wants them to be able to run around. Okay, and he wants to use all the fencing. So we know that our restriction is 800 meters of a perimeter. So we're not going to write out the formula for perimeter. What our focus is going to be first is this area. So the equation for area, we can say A at X, you can put A at W, A at whatever it is, okay? So let's label this diagram first. So we know that the width is going to be some value X, okay? And we can say let X represent the width. Okay, and instead of introducing a new variable, what we're going to do is we are going to think of an expression that talks about maybe the length, you want to call it, the length of this side with respect to X. So if you think about it, we have 800 meters of fencing, and this we could like just do on the side, 800 meters of fencing, but we've already used X amount for here, so minus X, and we've already used X amount for here. So really what's left over is 800 minus whatever we already used, 2X. So 800 minus 2X. So now when we take a look at the formula for area, we know area, again, side of the paper, this is just brainstorm over here. Area is length times width, right? So length would be 800 minus 2X, and width would be X. I'm actually going to put the width in front. I always like my monomial before my binomial. Okay. So if we were to expand this, we would get the formula 800x minus 2x squared. So now that we have our equation, what we want to do, and we can box this equation if you want, what we want to do is we want to find the maximum possible area. So maximum possible area, we're trying to find when the tangent equals 0, right? We're trying to find that max point. So let's find the derivative of a. So a prime at x equals derivative of 800x is just 800. And the derivative of negative 2x squared, we bring this 2 down, we get negative 4x. Okay, so we have the derivative, and now we want to find when this derivative equals 0. That's going to be one of our turnaround points. Okay, so 0 equals 400 minus 4x. We're going to bring over the negative 4x. It changes to 4x. And then we're going to divide out that 4. Okay, so I get that there is going to be a max or min value, likely for this question, a max value, when the width is 200. That's 200 meters. So now what we have to do is we have to think back to 3.2, and we want to talk about what domain this area exists on. Okay, so let's talk about the domain. So the width of x cannot be 0, but it can just be slightly greater than 0. If you had a 0 for either the length or the width, when you plug it into this area formula, it'd be 0 times some number, which is going to give us 0. If the area is 0, it doesn't actually create a rectangle. So we're going to use 0, but we're going to use the inequality without the underline there, without the equal. Okay, so we've taken into account what x could equal. Now, for the other side of the domain, let's talk about the larger value, right? So let's talk about when 800, this is at the side of my paper, minus 2x equals 0. Because 800 minus 2x just has to be just slightly greater than 0. So we would have 800 has to be greater than 2x, right? Move that over. Divided by 2, and we get 400. Okay, so x is going to have to be between 0 and 400. 400 because if we were to have this length, or sorry, the width, I need to say width because we use the variable x, which is our width. If we have the width of 400, what we'd essentially have is 400 here and 400 here, leaving no fencing available for the length. Again, that would set the length to 0, and we can't have that because then we don't actually have a rectangle. Okay, so now what we have is we have three possible max or min values. Okay, we need to test. So let's go. We can say max or min can occur at x equals potentially 0, so endpoint 200, right, when we have a horizontal tangent, or 400, other endpoint. So those three are going to be the ones that we test. We're going to test A at 0, we're going to test A at 200, and we're going to test A at 400. And we're going to see what those equal. Okay, and again, 2 endpoints, and then when the horizontal tangent, we're subbing this into the original equation. So we're subbing in this into 800x minus 2x squared. So when I sub in 0, I get 0. And when I sub in 400, I get 0. We kind of already went over that. Even though our domain doesn't actually include it with this underline for the inequality, we have to test those. Okay? And when we sub in 200, we get 80,000. Okay, so obviously this is going to be our maximum value. And we can simply write, therefore, we have a maximum area of the field is 80,000 meters squared with the dimensions. Okay, so we have x equals 200, so that's 200 being like the length by, and then all you have to do is go back up here to the width formula, 800 minus 2x. You can do this aside of your paper. 800 minus 200, which is 800 minus 400, which is 400. So 200, let's go meters by 400 meters. Example 2, a piece of cardboard that is 60 centimeters by 30 centimeters. Okay, let's start by drawing that. Is being used to make a rectangular box with an open top. Okay, so what this means is that the corners are going to be cut out and the sides, like it's going to be folded along here, like these edges. And it's just going to be folded up. It's kind of like a pop case. Okay, it's going to look something like this, where if you were to break this edge here and unfold, this rectangle here would actually flap basically down, and the rectangle on this side would flap down, the rectangle on this side would flap down, and also on the other side, and it's going to give you one big rectangle. So what ends up happening in this scenario? Oh, I'll read the rest of the question. Determine the dimensions that will give the box the largest volume. So in the last question, we dealt with area, and now we're dealing with volume. Okay, so on the side of your paper, you can just recall volume is length, width, height. Okay, but we're not going to use L, W, and H. We're going to come back over here, and what's going to happen is these corner cutouts are going to be in the shape of a square. And we don't know how big the corner cutouts are going to be, so we can just call it X. So we can say like let X represent, and we can call it the height, okay, of the box. Okay, because once you fold these sides up, X becomes the height. So what's going to happen is now we have to actually take a look, like, okay, so if we cut out here and here, what's our new width? Well, it was 30, but we're taking away X and we're taking away X. So this is now 30 minus 2X. And going down to the other side here, the length, if we take away X here and we take away X here, what's only like the length from here to here? Well, we're going to get, and I'll write it up here, 60 minus 2X. Right, so 60 is the original. We're going to get rid of X, and we're going to get rid of X, which is 2X. And obviously that's subtraction. Okay, so let's list this. So the height is going to be X. Okay, the length is going to be 60 minus 2X. And the width is going to be 30 minus 2X. Okay. Now, the other thing we have to consider is the domain. So let's talk about that right now. I know I left it till the last question, but if we don't have a height, then we don't have a box. So the height is going to be between 0, but not including 0, and for this other value, I'm going to take the smaller of the two sides, which is going to be 30 minus 2X, against the side of my paper. Okay, 30 minus 2X has to be greater than 0. So bring that over. 30 has to be greater than 2X. Okay, so X has to be less than 15. If we're cutting out more than 15 centimeters, what's going to happen is we're not going to have enough of a width to cut. And then again, we don't have a box. So it has to be between 0 and 15. All right, so let's start with the equation. So volume at X is going to be length times width times height. Right, so the length, I always put the monomial first, so I'm going to put X, and then the length 60 minus 2X, and then 30 minus 2X. Okay, instead of doing that expanded version of product rule, I'm going to simply FOIL this and then expand the X into this. Okay, so 60 times 30 is going to be 1800. 60 times negative 2 is going to be negative 120x. 30 times negative 2x is going to be negative 60x. And negative 2 times negative 2, well, negative 2x times negative 2x is positive 4x squared. Okay, now I'm going to expand this x into every single term. Okay, so I get 1800x, negative 120 and negative 60 is negative 180. So I get negative 180x squared, and then plus 4x cubed. Okay, and I want to put this into standard form, which is just the 4x cubed first, and then the negative 180x squared, and then plus 1800x. So this is our expanded version of the volume of this box. Okay, so now let's go ahead and let's find the derivative of this. Okay, so we bring down the 3 and we get 12x squared. We bring down the 2 and we get negative 360x. And then 1800x, the x goes away and we just get 1800. So we want to know when the derivative equals 0. We want to know when we have a horizontal tangent because that's when a max or a min may occur, right? Remember, 2 endpoints and then any time the slope of the tangent equals 0. Okay, so we set the derivative equal to 0. What we can do so far is we can factor out a 12 out of each one of these terms. So we're left with x squared minus 30x plus 150. Okay, at this point, we need to factor because we need to solve for x, right? X is the height. When are we going to have a max or min height? So if we think about, and again, side of the paper, let's think about factors of 150, right? Coefficient of x squared is 1. So factors of 150 are 1 and 150, 2 and 75, 3 and 50, 5 and 30, 6 and 25, 10 and 15, and I believe that's it. Yeah, okay. So do any of these have the difference or add up to negative 30? None of them do. So at this point, we have to find factors a different way. We have to include quadratic formula. So we're going to go x equals negative b plus minus the square root of b squared minus 4ac all over 2a. There's no other way to solve for these x's. Okay, so our a value is 1, our b value is negative 30, and our c value is 150. So our x's are going to be 30 plus minus, okay, negative 30 squared minus 4, 1, 150, all over 2 times 1. Okay, so we're going to get 30 plus minus, and when we solve for what's under the bracket here, we get 30 squared minus 4 times 150. We get 300, root 300 over 2. We can go ahead and branch off. Right, we're going to have two answers, the plus minus. So we get x equals 23.7, and then x equals 6.3. And it's okay to go to 1 decimal. So when we think about what our max and min could be, max or min, so for this one specifically, we're looking for the largest volume. Okay, so we're only looking for a max. We are going to sub in the volume at the 2 endpoint 0 the volume at, I just go in order, 6.3, the volume at 15, and now come to think of it, 23.7 is not in the domain. Okay, so this is inadmissible. Not in domain. So we can go back up to this original equation here, the volume equation, and we can sub in V at 0, and we're going to get 0. We can sub in V at 15, and we're also going to get 0. And then we can sub in V at 6.3, and we get 5196. So now let's assess. Out of these three numbers, what is going to be the biggest number? Well, it's definitely 5196. So therefore, the maximum volume is 5196, and that's going to be measured in centimeters cubed with the dimensions. Okay, so x is the height, so x is going to be 6.3 centimeters by 60 minus 2x. We might need to go to the side of our paper. Okay, 60 minus 2 times 6.3. And we get 47.4 centimeters by, and then the width is 30 minus 2x. So again, 30 minus 2 times 6.3. We get 17.4 centimeters. So those are the dimensions. So example 3, Crystal and Shannon are both training for a marathon. Crystal's house is located 20 kilometers north of Shannon's house. So I'm thinking never eat shredded wheat. Okay, so we have Crystal's house is here, and we have Shannon's house is here. Okay, Crystal's 20 kilometers north. So this entire is 20. At 9 a.m. one Sunday, Crystal leaves her house and jogs south at 8 kilometers an hour. So now we don't just have 20 kilometers, we now also have a rate. Okay, so she's going to jog south at a rate of 8. I want to move this over. All right, there we go. Moved it over. So 8 kilometers per hour. At the same time, Shannon leaves, it's supposed to be her house, and jogs east. So she's jogging to over here, right? She's going this way at a rate of 6 kilometers per hour. When are Crystal and Shannon the closest together, given that they both run for 2.5 hours? Okay. So we want to know, where does Crystal end up? So maybe this point here, let's call this A. And where does Shannon end up? Maybe this point here, let's call it B, where they're closest together. So this is going to be the distance between A and B, where Crystal ends up and where Shannon ends up. And remember, this is like continuing, right? So it's like this. That's how they're running, right? Because Crystal's running down while Shannon runs to the right. So we want to know which of these lengths is basically the shortest. Okay, so let's write down some information, okay, to organize our thoughts. So Crystal starts at point C. So Crystal starts at point C. Okay, and reaches, we're going to call it point A after T hours. Okay, because these are quoted in kilometers per hour, let's just leave them in hours, even if it comes up as a decimal. like decimal 68 or decimal 75 or whatever, we'll convert it into minutes later. Okay. And then we're assuming that A and B are going to be the distance where the distance is the minimum. So the length of this node right here from C to A, so CA is actually going to equal 8, so 8 kilometers an hour times the number of hours run, and the distance is going to be 8t kilometers. Okay, I can't tell you exactly how many kilometers that is because we don't know what t is. We don't know how long they ran for. And then we know that AS is going to be the leftover. Okay, so we know that CS altogether was 20, but if we're taking away basically CA, we're going to get 20 minus 8P. We're going to get whatever this whole distance is minus the CA, and we're going to get what's left over, AS. And that's going to be that many kilometers. You can bracket that if you want as a binomial. So what we're doing now is we're quoting these distances of all of these lines or line segments with respect to t. And we can actually go back up here and we can say like let t represent the length of time of Crystal and Channing. So C and S running, the length of time that they run. Okay, so we talked about Crystal. That's in purple. Now let's talk about Shannon. So Shannon starts at point S. You can write that down if you want. Shannon starts at point S and reaches B after T hours. Okay, and because we're quoting this the same, like after T hours, we know that AB is going to be our shortest distance. So when we talk about AB, when we talk about SB, the length of SB is going to be 6 times however many hours run kilometers. Okay, that's going to be the distance between S and B. Okay, so when we talk about the distance of AB, what we're actually doing, if you think about it, back up to this diagram, AS is going to be 20 minus 8t, right? SB is going to be 6t. So when we talk about the distance of AB, we're actually going to use Pythagorean's theorem. Okay, so if you want to do this Pythagorean theorem. Okay, so we know this is generally a squared plus b squared equals c squared, right? C squared is going to be our AB. So a squared, let's call that AS squared. B squared, let's call that SB squared. And then our C squared is going to be AB squared. But our actual formula for AB, we're going to root the right-hand side and root the left-hand side. So our formula that we're going to be using for Pythagorean's theorem is going to be AB equals the square root of AS squared plus SB squared. That's kind of like an aside at the side of the paper. So let's use the formula AB, which is going to be the distance that they are apart, right? AB equals the square root of AS squared plus SB squared. Okay, so let's actually call this the distance at time t. And what we're going to do is we're going to use, so as squared is going to be 20 minus 8t all squared. Okay, that expression. And then SB squared is going to be 6t all squared. Okay, so now we have a formula of the distance in terms of t. Okay, so now let's just expand this first. Okay, I want to expand everything underneath this, this root sign. So when we expand the 20 minus 8t, remember we're not just squaring each of these components, we're actually doing 20 minus 8t times 20 minus 8t, just showing you on the side of the paper. Okay, so it's going to be a trinomial there. Okay, so I get 20 times 20 is 400. Okay, 20 times negative 8 is negative 160, but then 20 times negative 8 again, we're going to take two of those, so minus 320t. And then negative 8t times negative 8t is plus 64t squared. Okay, and then so that's 20 minus 8t squared, all expanded, plus 6t squared. We're going to go 6 squared is 36, and then that's going to be a t squared. So I'm going to rewrite this one more time. S at t equals, okay, so adding these, I'm going to add 64t squared and 36t squared. So I get 100t squared. And then I get minus 320t plus 400. Okay, so this is our equation for the distance at time t. Now what we want to do is we want to find the derivative of this. So the derivative of this is going to be, so I'm going to treat this root sign, instead of a root, I'm going to treat this as to the exponent 1/2. Okay? But I'm not going to rewrite it. So bring the 1/2 down, I get 1/2, and then I get bracket 100t squared minus 320t plus 400, because that's what's in the bracket. And then this bracket, because this is the root, that goes to the negative 1/2. Then I have to do the chain rule. So we're going to take the derivative of what's in that bracket. So we get 200t minus 320. So I'm going to just simply go ahead and rewrite this. This bracket here to the negative 1/2 is going to make that go down into the denominator, and then we can write it as a positive exponent. So in the denominator, we're going to have a 2, and then we're going to have a bracket 100t squared minus 320t plus 400. And then in the numerator, we're going to have 200t minus 320. Oh, and then this is to the 1/2. Okay, so this right here is our derivative. So in the numerator, I'm going to go ahead and factor out a 2, and I get 100t minus 160. Okay, over 2 bracket 100 t squared minus 320t plus 400 to the 1/2. And of course, we can cancel out those 2's. So what we want to do is we want to take that and we want to determine when does the derivative equal 0. So 0 equals 100t minus 160 over this denominator, 100t squared minus 320t plus 400, all to the 1/2. Okay, so when we multiply up, so cross multiply, this goes away. We're simply solving for when the numerator equals 0. Okay, so we can go ahead and bring over the negative 160, and we get 160 equals 100t. And then we divide both sides by 100, and we get t equals 1.6. So now what we want to do is we want to consider the domain. Okay, so when are these ladies the closest together? We're going to do this on the domain between 0 and 2.5 hours. So what we're going to do is we are going to test the numbers. We're going to test the distance at time 0, the distance at time 1.6, and the distance at the time 2.5. And we're going to see when they're the closest. So obviously the smallest number. So the distance at 0, they're 20 meters away from one another. The distance at 1.6 is 12 and 2.5 is 15. So this is clearly the smallest number here. So we can say, therefore, the minimum distance is 12 kilometers at 1.6 hours. And if you want 1.6 hours in minutes, what we want to do is we want to do 1.6 times 60. Remember, minutes is base 60. So, or 96 minutes. Okay. And if you refer back up to the original question, it did say that they left at 9 a.m. So if you think about it, or at, so if they left at 9 a.m. and you ran for 96 minutes, so that's 1 hour, 6 minutes, so it's 10:06. Oh, sorry, 1 hour, 36 minutes, 10:36. So 10:36 a.m.